This is section 4.5a, sine and cosine graphs. So with this section we're really getting into the heart of trigonometry, and this section and the following ones are very important for calculus, because in calculus you're going to be using the graphs of the trig functions and you'll be analyzing the graphs. So it's very important to be familiar with the graphs, be able to manipulate them. So make sure you are diligent and take good notes in this section. First, let's talk about the characteristics of waves in nature. Now, we see waves in a lot of places in nature. In fact, usually, or every second, while our eyes are open, we are seeing, without realizing it, we're seeing light waves. Light waves are hitting our eyes. And so, as you may know, light consists of photons moving in the pattern of a sine wave, a wave just going up and down like the wave on this screen. So light is a wave, sound is a wave. You know, when we are in the ocean and go surfing or boogie boarding, we're seeing waves. So there are a lot of waves in nature. And so these are just some of the elements of those. The crest is the high part. The crest, of course, refers to the whole upper part, but in math, when we're talking about crests of waves, normally we're referring to the highest point of the wave. The trough is the lowest point of the wave. The height of the wave is the distance from trough to crest. The amplitude is half the height. The amplitude is half the height. The wavelength is the distance from crest to crest, literally the length of the wave. And the distance, or time, is what is on the x-axis. Now, this can sometimes be a little confusing to students, because you're like, well, why is it distance or time? The reason for that is it depends on how you're considering the wave. If you're considering the wave as a function that's moving through time, then your x-coordinate would be time. But if you're just considering the wave statically, that is, just measuring its distance, then the x-coordinate would be distance. All right, so in physics, you're going to sometimes see it with distance in the x-coordinate, and sometimes you're going to see it with time as the label of the x-axis. But in either case, wavelength is an indication of how long a wave is, as its name would suggest, and it's measured from crest to crest. Now, period only applies when we're talking about time in the x-axis, because period is how long it takes for a cycle to complete. Now, by cycle, I mean going from, for example, crest down to trough, back up to crest. That would be one full cycle. And so, whereas if we're talking about distance, wavelength is the physical distance from crest to crest. When we're talking about time, period is the amount of time that it takes for one cycle to complete. The amount of time it takes for one cycle to complete. That would be period. All right, now we're going to talk a little more specifically about characteristics of sine waves on the unit circle. Now we've done the unit circle before, so that's nothing new. But let's look at this example. This is a sine wave. This is simply the sine function, y equals sine x, graphed out. And if I have the graph of y equals sine x, I can identify its elements. I've got wavelength, which is the arc length per cycle. Recall, of course, that on the unit circle, this is the beauty of the unit circle, on the unit circle, the magnitude of the arc length equals the magnitude of the angle. Okay, length, of course, is not the same as angle, but the magnitude, or the measurement, how small or great that arc length is, on the unit circle is the same exact number as how small or great the angles are. All right, the wavelength then is the distance, or the arc length, from crest to crest. The period normally the period is measured from the equilibrium point. The equilibrium point is just where, it would be the middle of the graph. You could think of it as the middle of the graph. And so period is normally measured from where a function first hits the equilibrium point until it completes its cycle at the same equilibrium point. Okay, so notice that if you follow where the mouse arrow is, the sine wave goes up and then down and then up. And so if I measure from here at the equilibrium point, it goes up and then down and then up. That complete cycle is the period. And when we're talking about the unit circle, the period is radians per cycle. How many radians you go through in a cycle? So with this sine function, the sine function would be called periodic, which means that it repeats. And it's periodic also because in one period or one cycle, it goes through 2 pi radians, 2 pi radians. And we can clearly see on this graph that it completes a cycle in 2 pi radians. 2 pi is about 6.28. And here we can see that we have 6.28 because each of these tick marks stands for 1/2. So this here where I'm pointing with the mouse arrow is 5.5, and now where I'm pointing with the mouse arrow is 6, and 6.28 is this point here at the equilibrium point at the end of one cycle. And so there are 2 pi radians per cycle for the sine wave. The amplitude is half the distance from crest to trough, or if you like, half the height of the wave. And the frequency is the number of cycles per radian. So it makes sense if period is measured in radians per cycle, well, then 1 over the period is cycles per radian. And frequency is by definition either cycles per radian or cycles per second if you're talking about time on your x-axis. Here, of course, for this particular graph, what's represented on our x-axis is both the angle and the arc length, since those are of the same magnitude on the unit circle. Okay, so in this particular case, frequency represents cycles per radian, But there will be problems that you'll see, especially in physics. You'll see frequency as hertz or cycles per second. The parent sine graph. This is what the parent sine graph looks like. And even though you've seen the sine function graphed before, it is helpful to review that and to make sure that we understand all of its elements. We often call the equilibrium points intercepts because that's where they cross the x-axis, so you could think of them as x-intercepts. We call the crest a maximum. We call the trough a minimum. Okay, and then another important thing about this graph is notice that this graph has 5 critical points. The beginning of the period, the quarter period, the half period, the 3/4 period, and the full period. Okay, this is going to be something that you're going to use a lot in this section, the 5 critical points. The start of your period, the quarter period, half period, 3/4 period, and full period. Of course, as I mentioned in the last screen, the period is 2 pi radians. And the critical points are labeled with their x and y coordinates. Notice also that this function has a domain and range. Of course, this is only a portion of the sine graph. If you look over to the left of the screen where my mouse arrow is now, I could trace out where the rest of the graph would go. It would go down and then up and then down and up. And then if I go over here and continue it, it would go up and then down and then up and then down. All right, so the domain of the sine function is all real numbers. Every x coordinate works. All right, if I'm talking about x in radians and I put in any x in radians, there will always be a sine function for it. Now the range of the sine function, as you can see, is from -1 to 1 because it keeps oscillating between those two values. An important fact about the sine curve is that sine negative theta equals negative sine theta. Now, we did cover even and odd briefly in a previous chapter, in case you're rusty on it. If f of negative x equals negative f of x, then we're dealing with odd. If f of negative x equals f of x, then we're dealing with even. You could also think of odd in terms of symmetry. The sine graph is symmetric about the origin. And we can clearly see that because if you look at the mouse arrow now, you can see that the sine curve is going to continue below the x-axis, and then it's going to come back up, and then it's going to go back down, etc. But the pattern that it makes is symmetry about the origin. Symmetry about the origin. Let's look at this angle here. This angle here is the angle pi over 2. The sine of pi over 2 is 1. Well, looking at the fact of sine negative theta equals negative sine theta, we can, even if you want to do it on your calculator, you can. Sine of negative pi over 2 is negative 1. Sine of negative pi over 2 is negative 1, and that confirms this fact that sine of negative theta equals negative sine theta. So just remember that the sine function is odd. The sine function is symmetric about the origin. The parent cosine graph. As you can see, the parent cosine graph is very similar to the parent sine graph. In fact, they have the same exact shape, except that they're out of phase with each other by exactly pi over 2 units. So now we'll get into that a little more later. This has to do with the fact that they're cofunctions. But in any case, we can see that the domain is all real numbers, the range is from -1 to 1, the period is 2 pi, and we still have critical points of beginning of the period, quarter period, half period, three-quarter period, and full period. But notice that the x and y coordinates for those critical points are different for the cosine graph. The cosine function is even, which means that cosine of negative theta equals cosine theta. And if you want to think about it this way, you could say that the cosine graph is symmetric about the y-axis. Symmetric about the y-axis. We can again prove this to ourselves. Let's say we look at the pi over 2. Pi over 2 is our x-coordinate. That is an angle of 90 degrees. Pi over 2 in radians. The cosine of pi over 2 is 0. And if I reflect this whole curve in the y-axis, I can clearly see that the function, once it hits the point 0,1, is going to go back down, and then up, and then down, and then up, etc. But sure enough, the cosine of negative pi over 2, which would be over here to the left, cosine of negative pi over 2 is 0, which is also the same as the cosine of pi over 2. All right, so the cosine function is even, that is, it is symmetric about the y-axis. Let's look at properties of the parent sine and cosine functions. The graphs of y equals sine x and y equals cosine x have these properties. 1, the domain is negative infinity to infinity, all real numbers. The range is -1 to 1, inclusive, includes the endpoints. The graph is a smooth curve. Each function has a period of 2 pi radians, and each function has a frequency of 1 over 2 pi. Okay, so remember that a period, as seen earlier, is measured in radians per cycle, whereas frequency is cycles per radian. Graph of the parent sine function. Okay, so to sketch the graph of y equals sine x, you first plot the key points, the 5 critical points. These are at x equals 0, 1/4 period, 1/2 period, 3/4 period, and full period. All right, so up here in the first row of the table, I've got my x coordinates. Down here in the second row of the table, I've got my y coordinates. And so at the beginning of the period, when x equals 0, the value of sine x equals 0. At quarter period, when x equals pi over 2, the value of sine pi over 2 is 1. At half period, when x equals pi, the value of sine pi is 0. At 3/4 period, when the value of x is 3 pi over 2, the sine of 3 pi over 2 is -1. And at full period, when the value of x is 2 pi radians, the value of sine 2 pi is 0. So then we connect the points on the graph with a smooth curve that extends in both directions beyond the 5 points, and that is going to look like this. Okay, so you can sketch any sine or cosine function, and in fact any trig function, once you know the critical points. Okay, so going back to our table here, we've got one point of 0, 0. That would be right here, where I'm circling with the mouse arrow. That's the point 0, 0. Then I have the point pi over 2, 1, x-coordinate pi over 2, y-coordinate 1. That's right here. And I have an x-coordinate of pi over 2 and a y-coordinate of 1. Next critical point, x-coordinate pi, y-coordinate 0. Next critical point is x-coordinate 3 pi over 2, y-coordinate negative 1. And finally, x-coordinate 2 pi, y-coordinate 0. Then what I can graph directly with the critical points is in red, and of course what I extend is in black. And so this is the basic strategy for sketching any trig function. For now, we're just doing sine and cosine. Graph of the parent cosine function. To sketch the graph of y equals cosine x, first plot the key points. These are at x equals 0, quarter period, half period, 3/4 period, and full period. So keeping in mind what we did on the last screen, do this sketch on your own using the same method, and then resume when you have your answer. Okay, so you should have come up with this as your table and these values. Then you connect the points with a smooth curve, extend in both directions, and this is what you have. All right, so I'm sure you were able to do that on your own because it used the same exact steps as what we did on the last screen. But this is just practice to become very familiar with the cosine function, the sine function, and with their symmetry. Notice that here I have y-axis symmetry because the cosine function is an even function. Let's review that concept because it doesn't hurt to. Pi over 2, cosine pi over 2 is 0, and cosine of negative pi over 2 is 0. Therefore, the function is even. With the sine function, I'm just going to quickly go back. With the sine function, you can see that it's odd. That is, it's symmetric about the origin. Because when I look at this pi over 2, for example, the sine of pi over 2 is 1, but the sine of negative pi over 2 is negative 1. Therefore, it's an odd function, symmetric about the origin. Okay, I'm going to quickly go on to where we were. Okay, so these are basic graphs of the sine and cosine. Those are the parent sine, the parent cosine. And now we're going to look at the child functions. That is, all the derivative functions based on the parent functions. First, let's look at the amplitude. The amplitude of y equals a sine x, or y equals a cosine x, is half the distance between the maximum and minimum values of the function. Okay, so if you like, you can call the maximum your crest and the minimum your trough. Half of that distance, or half of the wave height, is the amplitude. Amplitude, in mathematical terms, is the absolute value of a, when a is whatever constant is being multiplied by your sine function or your cosine function. If the absolute value of a is greater than 1, the amplitude stretches the graph vertically. Remember, we've done vertical stretching before. If 0 is less than absolute value a is less than 1, the amplitude shrinks the graph vertically, and we've done vertical shrinking before. It's the same principle. If a is less than 0, the graph is reflected in the x-axis. Okay, and we've also done that before, where if, like when we were doing quadratic functions, if you're dealing with the standard form, ax minus h squared plus k, the sign of a determines whether it points up or down. All right, let's look at some examples. This is our simple parent sine x, Let's look at what would happen if we multiply it by 2. Y equals 2 sine x. The 2 doubles the amplitude. And so now instead of an amplitude of 1, like the parent sine x, I have an amplitude of 2 for the child function 2 sine x, 2 sine x. Notice also that since 2 is greater than 1, I have a vertical stretching. Let's look at y equals 1/2 sine x. Y equals 1/2 sine x. Well, I can see that I've got a vertical shrink. I've cut the amplitude in half. Y equals 1/2 sine x. How about y equals 4 sine x? This is also a vertical stretch. I've quadrupled the amplitude. And finally, y equals -4 sine x. I see that I have a vertical stretch and an x-axis reflection. Example, sketch the graph of y equals 3 cosine x on the interval -pi to 4 pi. Remember that when we're talking about sketching graphs on intervals, the intervals represent x-coordinates. So from the x-coordinate of -pi to the x-coordinate of 4 pi, sketch the graph of y equals 3 cosine x. Okay, I'm going to walk you through part of this and then you'll do the rest on your own. Remember that the basic strategy is find the 5 key points, then graph one cycle, then repeat the cycle over the interval. Okay, so pause the video, try and do this on your own. Remember, of course, first to set up the table with the 5 key points. And then, as we did in a couple of earlier examples, you're going to sketch. Keep in mind that here we have a tripling of amplitude, a vertical stretch, and that's what the 3 does. So pause the video, do that on your own, then resume when you've completed it. Okay, so here's what your table looks like. You've got 0, which is the beginning of the period, pi over 2, quarter period, pi, half period, 3 pi over 2, 3/4 period, and 2 pi full period. The values are 3, 0, -3, 0, 3, so you've got your critical points. Then you can simply graph those critical points for one cycle. And then all you do is you extend that cycle over the interval. And since our interval is -pi to 4 pi, I only have to graph from -pi to 4 pi. The period of a function is the x-interval needed for the function to complete one cycle. For b is greater than 0, the period of y equals a sine bx is 2 pi over b. Okay, so what we have going on now is we have a b coefficient affecting the period. Okay, so if you see x multiplied by anything within the sine function, then it's going to modify the period, and it modifies it by the amount of 2 pi over b. Now let's see why that's true by observing some graphs. For b is greater than 0, the period of y equals a cosine x, or cosine bx, is also 2 pi over b, because sine and cosine are very similar. If b is greater than 1, the graph is shrunk horizontally. Okay, so let's look at all of these elements in action. We've got our x and y axes. This is the basic parent sine function, y equals sine x. It has a period of 2 pi, of course. Now, what about the function y equals sine 2x? Notice that we have a b term here now. We have a b, the b is 2. And so we have sine 2x. Notice that sine 2x has a period of pi. It has a smaller period. That means that it needs less radians to complete a cycle. And if we observe the graphs, which you can also verify on your own calculators if you wish, if we observe the graphs, we see that the difference in period is given to us by 2 pi over b. If I look at my parent function, y equals sine x, the parent has a period of 2 pi, just as I would expect. But the child function, sine 2x, has a period of pi, which is the same as 2 pi over 2. 2 pi divided by 2 equals pi. And in this case, 2 pi divided by 2 is the same as 2 pi over b. If 0 is less than b is less than 1, the graph is stretched horizontally. Okay, so notice that since we shrunk up the period, we can call this a horizontal shrink in the graphed example. But if b is between 0 and 1, then I'm going to have a horizontal stretch. In other words, the period is going to be bigger. Let's look at an example of that. I have my basic cosine function here with a period of 2 pi, as I would expect. And now the child function that I've graphed here is y equals cosine 1/2 x. 1/2 is my b. It's between 0 and 1. It's fractional. And I have the effect of the period getting wider, which is also called a horizontal stretch. And notice that 2 pi over 1/2 equals 4 pi. 2 pi divided by 1/2 is 4 pi. And that's my 2 pi over b. Okay, so make sure that you understand horizontal shrink and horizontal stretch before you go on to the next screen. If you look at the graphs, you'll see why 2 pi over b is true. 2 pi over b is true because it confirms what we see on the graphs, and that, of course, is the easiest way to prove it. Actually, it's not the kind of thing you need to prove. It's just a fact. It's something that's based on observation. Example, find the amplitude and period of y equals 2 sine negative 3x and sketch its graph. All right, I'm going to get you started on this example and then you'll do the rest. Rewrite the function in the form y equals a sine bx with b is greater than 0. All right, so basically all this is telling us is you want to get rid of that negative within the parentheses because it's easier to work with something when the negative isn't in there. And for that, we can just use the fact that sine negative x is the same as negative sine x. And so rewriting this function gives us y equals 2 sine negative 3x is exactly the same as negative 2 sine 3x. Okay, so keeping that in mind, you can simply see, or very clearly from the problem, see that the amplitude is 2 and the period is 2 pi over b. My b is 3, and so the period is 2 pi over 3. 2 pi over 3. All right, now pause the video. Do the rest on your own. Remember that you're going to find your critical points. Also keep in mind that your critical points, or the divisions, are going to be different now because, of course, a quarter period of 2 pi over 3 is not the same as a quarter period of 2 pi. So keep that in mind when you're setting up your chart, and then resume if you get stuck or once you have your final graph. Okay, so calculate the 5 key points. This is the most important step. And don't worry if you had to resume because you got stuck, or if you maybe didn't get these right values, because I can easily explain how we came up with it. Recall, of course, that the 5 key points are beginning of the period, quarter period, half period, three-quarter period, and full period. Well, if I know that my period is 2 pi over 3, because 2 pi over b in this particular case is 2 pi over 3, well, then a quarter of 2 pi over 3 is the same as 1/4 times 2 pi over 3, and that, of course, is the same as 2 pi over 12, and 2 pi over 12 reduces to pi over 6. Therefore, my quarter period marker is pi over 6, the angle pi over 6. The same is true with all the critical points. 1/2 of 2 pi over 3 is the same as 2 pi over 6, and that, of course, reduces to pi over 3. 3/4 times 2 pi over 3 is the same as 6 pi over 12. That, of course, reduces to pi over 2. And, of course, the full period, or just 1 times 2 pi over 3 is 2 pi over 3. So that explains the x-coordinates of my critical points. And the y-coordinates is simply just plugging in the values. That's the easy part. You just plug in the x-coordinates of your critical points, and you can easily find the y-coordinates. And so then graphing those critical points, all you have to do is plot, then you connect the dots and extend, and you have your answer. Classwork, page 328, numbers 37 to 44 all, and see you in class.